Scaling and normalizing data, making features comparable. In this lesson, we will learn how and why to scale and normalize data using Pandas. These techniques help prepare real-world data for machine learning models and better visualizations. We will see practical ways to apply them, understand the differences, and know when to use each. Let us dive in. Running the cell now. It is helpful to hide warning messages when teaching. We hide warnings in our notebook so we can focus on the main output. We bring in Python's warnings library. Import numpy as np. We set the random seed to 42 for reproducibility. This command tells Python to hide all warning messages. Running the cell now. No output is shown here because this code block sets up the environment by importing libraries, fixing the random seed for reproducibility, and suppressing warnings. This ensures that subsequent scaling and normalizing operations run smoothly and produce consistent, clean outputs for clearer learning. You can try toggling warnings off and on. This keeps notebooks less cluttered. Let us get some real data to practice scaling and normalization. We add a comment describing the step. We make Pandas available for our work. We set a web link to the Titanic CSV file. We read the file into a data frame called df. A data frame is a table of data. This shows the number of rows and columns in the dataset. We preview the first few rows to see what the data looks like. Running the cell now. This output shows the Titanic dataset with 891 rows and 12 columns, providing a snapshot of key features like passenger class, age, fare, and survival status. Noticing these columns helps us understand which numeric features may require scaling or normalization to make them comparable for machine learning models. This initial exploration sets the stage for transforming these diverse features in the next steps. Try looking up the Titanic dataset's columns on the web. What kinds of values would you expect to scale here? Why scale and normalize? Raw features in datasets may have very different ranges. For example, age might be 1 to 80, fare might be 0 to 500, and p-class is 1 to 3. Machine learning models often perform better when features have similar scales. Scaling changes the range or spread of numbers, while normalization often means squeezing all values to be between 0 and 1. Running the cell now. Let us identify which columns are numeric. We will need those for scaling. We add a comment to label this step. This gets the names of all columns containing numeric values. We print out the list to see which columns are numeric in our dataset. Running the cell now. This output lists all the numeric columns in the dataset, which is crucial for identifying which features may require scaling or normalization. Notice that columns like age and fare have different ranges compared to categorical-like numeric columns such as p-class or survived. Understanding these numeric features helps us apply scaling techniques appropriately to improve model performance. Observe which columns you might use for scaling. Age and fare are good examples. Let us see the spread of values in our numeric columns using describe. We label what we are doing here. We summarize each numeric column with basic statistics like minute, max, mean, and standard deviation. Running the cell now. This output provides a snapshot of the numeric feature ranges and distributions before scaling, showing wide disparities. For example, fare ranges from 0 to over 512 while p-class only ranges from 1 to 3. Notice how features like age and fare have much larger means and standard deviations compared to SIB-SP or PARCH. This highlights why scaling is crucial, to bring all these features to a similar scale, helping machine learning models learn effectively without bias toward features with larger numeric ranges. Notice how some columns have maximums much bigger than others. This can confuse models if not handled. MinMax scaling, stretch values to a given range. MinMax scaling takes each value, subtracts the column's minimum, and divides by the column's range. The result is always from 0 to 1. It is a good choice for many machine learning models and when all features should have the same importance. Running the cell now. Let us manually scale age and fair using the MinMax approach. We say what the next code block does. We make a copy of the age and fair columns as a new data frame for scaling. We loop through each selected column to apply the same calculation. Each value is transformed so that the minimum becomes 0 and the maximum becomes 1. We peek at the first 5 scaled values. Now, everything is between 0 and 1. Running the cell now. Here we see the age and fair column scaled between 0 and 1, confirming the MinMax scaling formula worked as intended. Notice the values no longer represent original units but their relative position in each feature's range, which standardizes the scale and helps models weigh features equally. This output demonstrates how the scaling transforms varied ranges into a uniform scale for better model performance. Try this method with more columns. Do all values now fall in a similar, smaller range? Sometimes a column has missing data. Let us check for that before scaling. We ask what happens if a column has missing data. This line counts the number of missing or null values in the age and fair columns. Running the cell now. This output shows the count of missing values in the age and fair columns before applying MinMax scaling. Notice that aged has 177 missing entries, while a fair has none, highlighting the need to handle these missing values first to avoid errors or skewed scaling results. This check ensures the scaling process works correctly and consistently across all data points. If you see missing values, think about how you want to handle them, by filling, dropping, or leaving as is. A common approach is to replace missing values with the median, so scaling is not affected. This step is about handling missing data. We fill missing age and fair values with each column's median. The median is the middle value in a sorted list. We check again that there are no missing values now. Running the cell now. This output shows that all missing values in the age and fair columns have been successfully filled with the median values, as indicated by the 0 count of nulls. This step is crucial because MinMax scaling requires complete data without missing values to accurately rescale features between 0 and 1. By ensuring no nulls remain, the code prepares the dataset for reliable and consistent scaling in the next step. Try filling with the mean or another number. See how it changes the scaled data. Standardization, set mean to 0 and standard deviation to 1. Standardization transforms numbers so each feature has a mean of 0 and a standard deviation of 1. This is helpful when features have outliers or very different distributions. Mathematically, each value is subtracted by the mean, then divided by the standard deviation. Running the cell now. Now let us standardize age and fair. This step shows how to standardize data. We copy our filled data frame so we do not lose earlier work. For each column, we subtract the mean value then divide by the standard deviation. As a result, the data centers at 0 and spreads out based on standard deviation. We check that the mean is almost 0 and standard deviation is very close to 1 for each column. Running the cell now. The output shows that after standardizing, both the age and fair columns have means effectively equal to 0 and standard deviations equal to 1, confirming the transformation worked as intended. This ensures features are on the same scale, which is crucial when dealing with variables that originally had very different ranges or outliers. Notice how the small mean values reflect computational precision limits but are practically 0, emphasizing the success of standardization. Standardized features make a big difference in models like logistic regression and clustering. Libraries like scikit-learn can do feature scaling in one step. This code uses scikit-learn to scale features efficiently. We import the needed classes from scikit-learn.preprocessing. Here, we create a MinMax scaler object that handles the scaling. We apply the scaler and get back a data frame with new scaled values. Peeking at the first few rows, you can see the results are identical to the manual way. Running the cell now. This output shows the result of MinMax scaling, where the age and fairer features are rescaled to a range between 0 and 1, rather than standardized with mean 0 and standard deviation 1. Notice how the values now fit within this normalized range, which contrasts with standardization but is another common scaling method. This helps us compare the effects of different scaling techniques in a lesson. Try switching to standard scaler for standardization in one line. The robust scaler is another handy tool for scaling data safely, even with outliers. Here we focus on scaling methods that ignore outliers. We bring in the robust scaler from scikit-learn. We set up the robust scaler object. This line applies the robust scaling to age and fair columns. Looking at the summary stats, you will notice that the data is less affected by extreme values. Running the cell now. The output shows the summary statistics of the age and fairer features after applying robust scaler, which centers the data around a median of 0 and scales based on the interquartile range. Notice that the means are close to 0, but the standard deviations vary slightly because robust scaler is less sensitive to outliers compared to standard standardization. This demonstrates how robust scaler helps normalize features while minimizing the impact of extreme values, as intended in this lesson. Try adding artificial outliers and seeing how each scaler is affected. Let us see what happens when we plot the fair column before and after scaling. Now we will compare different scaling methods using a chart. Here we bring in matplotlib to make plots. We set the chart size to be larger for clarity. This histogram shows the original fair data's distribution. This histogram shows the scaled fair values using MinMax method. This adds the standardized fair values to the chart for easy comparison. We use a legend so the color key is clear. The chart title quickly explains what the viewer is seeing. This displays the chart for visual inspection. Running the cell now. This histogram compares the distribution of the fair feature before and after scaling. Notice how the original fairs are spread unevenly with some large values. MinMax scaling compresses all values between 0 and 1, while standardization centers the data around 0 with a spread defined by the standard deviation. This visual confirms that standardization effectively shifts the mean to 0 and adjusts the scale, making features with outliers more comparable. Look for differences in the spread and center of each distribution. When should you scale or normalize? Scale features when you use algorithms that compare numerical values, like k-means, k-nearest neighbors, linear regression, or neural networks. Normalization is great when you need everything between 0 and 1, or are working with images and pixel data. Standard scaling is better for most classic models, especially if data is not in the same range or has outliers. Running the cell now. Now it is your turn to try. Pick a numeric column, and we will scale it together. This challenge lets you decide which column to scale. Here we ask for input to pick a numeric column from the dataset. If your pick is in the list of numeric columns, we continue. MinMax scaling is applied to your chosen column. A message prints to say which column is scaled. We show the first few scaled values so you can check the results. If the column is missing or not numeric, a message tells you so. You can always try with a different column. Running the cell now. This output shows the MinMax scaled values for the SIB-SP column, with all values now ranging between 0 and 1. Notice how the scaling transforms the original counts of siblings' spouses aboard into a normalized format, making it easier for algorithms like k-nearest neighbors to compare these features fairly. This demonstrates how normalization prepares data for models sensitive to different numerical ranges. Try this with other datasets or columns. Did MinMax scaling work as you expected? Be sure to subscribe and click the bell for more data science lessons on YouTube. Let us practice feature scaling for a simple Titanic survival prediction model. Now we put scaling into a context for model training. Here we import a tool to split data into train and test sets. We choose age and fare, using the median to fill any missing values. This sets up our target variable, which is whether each passenger survived. We split data for fare model testing, using 20% as the test set. We bring in standard scaler, which standardizes features for modeling. We fit the scaler on the training set and transform it to have mean 0 and standard deviation 1. The same transformation is applied to the test set so our model can work reliably. We print the first few scaled training values to see how it looks. Running the cell now. Here we see the first 5 rows of the training features after standard scaling, where age and fare are centered around 0 with a standard deviation of 1. Notice how values now spread above and below 0, which helps algorithms like logistic regression treat both features equally despite their different original scales. This step prepares the data for models sensitive to feature magnitude, improving training stability and performance. Try using other scalars in place of standard scaler and see how model results change. Experimentation is key. Scaling is very useful, but you should not do it on everything. Let us discuss when not to scale. Here we get all the object or category or text columns. This lists out the names of the categorical columns in our data. This clear message reminds you not to scale columns that are not numeric, such as names. Running the cell now. Here, the code identifies categorical columns like name, sex, and ticket that should not be scaled. Notice how these columns contain labels or codes, not numerical measurements, reinforcing the lesson point. Scaling is for numerical features, while categorical data should be handled differently to avoid distorting the information. If you scale something like a ticket code, your analysis will likely make no sense. Scale only real numbers. Quick reference table. Technique use case outlier sensitivity range. MinMax scaling neural nets, images, KNN models sensitive 0 to 1. Standardization regression, clustering, ML pipelines not sensitive mean equals 0, SD equals 1. Robust scaling outlier heavy datasets resistant centered. Check this table to pick the right scaler for your scenario. Running the cell now. Sometimes, we get errors like value error. Here is what happens if we try to scale the wrong kinds of data. This line introduces the topic of troubleshooting value errors and shape mismatches. Start a try block to attempt the following operations and catch potential errors. Create an instance of MinMax scaler to scale numerical features. Attempt to apply scaling to the fare and sex columns from the data frame. Catch any exception that occurs during scaling and assign it to variable e. Print out the error message to understand why the scaling failed. Running the cell now. This error occurs because the MinMax scaler expects numerical input, but the sex column contains categorical string values like male. Notice that scaling techniques require numeric data, highlighting the need to pre-process or encode categorical variables before applying scaling. This reinforces the lesson that MinMax scaling is intended for continuous features, not categorical ones. Always double-check your data frame columns and their types before scaling. Review: what did we learn? We explored different ways to scale and normalize data in Pandas. We learned when to use MinMax, standard, and robust scaling. We saw how to pre-process real data before modeling. We practiced with visualizations and troubleshooting tips. Ready to apply these to your own projects. Running the cell now. Thank you. Next steps. Try scaling features in other datasets. Practice what you learned. Subscribe to the channel for more intermediate Pandas tutorials, and do not forget to hit the notification bell to stay up to date. Happy coding! Running the cell now.